since we haven't done it at all, here's where it comes from. So another way to write this is the square root of x squared, which obviously we can just immediately simplify, but that way it's always positive. And I guess technically this should be reversed so that we don't run into issues with square rooting, but like that. So it does the same thing as what absolute value does, but now we can take the derivative of it. So let's walk through that. What is the derivative of that?
2 over, wouldn't it be 2x over 2 root?
Just 2.
2 over x.
No? Okay, so we better just do it. So if we do the absolute value, that's 1 over root x squared.
Yeah.
Okay? And then we do the chain rule and do the inside times 2. Okay?
Yeah.
Wait, what?
Like, why isn't it 2x?
Y is what, 2x?
Why isn't it 2x?
It is. It's 2x. I'm sorry.
Okay.
It should have been 2x. Anyway, so this simplifies to x over square root of x squared, but we substituted square root of x squared for absolute value of x. So we'll go back to that. Okay? So this will kind of represent, because in our problem, and you guys will see it when you do it, I don't remember the exact numbers. It might be on here, in fact.
Square root of x plus 3.
Yeah, I don't see it on here.
That makes sense because it's always, like, your slope's always going to be either 1 or -1.
Yeah. It was just funny because we came across it. I think I put it in the warm-up maybe, and then it was like, wait a minute, we've never done an absolute value derivative. And so we kind of struggled through that a little bit. Anyway, I don't see it on here. It is on here somewhere, but so point is that let's say it was take the derivative of 2x minus 3. So this is the general form, but we do still have to take the derivative of the inside. So that's kind of what we were seeing. It was a 2 parts, it had a subtraction in between 2 absolute values, like maybe it was this, something like that, okay? And so with the subtraction, you still use the sum or difference property of derivatives, so you take the derivative of each one. But think about taking, like, well, do you guys want to try telling me before I write it? Think of U substitution and the chain rule is how we'll end up doing this.
Just say 2x minus 3 equals 0.
Yep. On this side, and then maybe over here put b equals 2x if we do what?
2x minus 3 over the
Yeah. So 2x minus 3 over the absolute value of 2x minus 3. So that's just rewriting this with u plugged in. Times 2. Okay? And then minus, and then scoot that over. How about this one?
2x over 2x.
Also times 2. Anyway, okay? So this would be worth memorizing, and then just know that it represents something you could use U substitution with and the chain rule and stuff. But yeah, because we tried to think through it, like, what if we did this, and then we looked, and it was like, whoa, where did that come from?
Yeah.
Now we know. And it does make sense once you kind of see it, but I think if it was me, I would go write that on that. I don't want to take time to pull it up. Do you remember at the end of unit 4
That one time. it was
Unit
over.
3, where we had written out just on those blank lines all the different derivative rules. That's kind of where I'm thinking of mine being collected. I would write it there. Just to have. That was super surprising. I was like, wait a minute, we've never even done this. You might come across something else when you do the rest of it. I don't think so. I think that was the only thing. So let's talk about topic 5.6. So concavity. What do you remember about it from pre-calc?
Which way the curve is, yeah.
Okay, good. So we'll have this kind of slick little trick to check now instead of. How did you do it in pre-calc?
We were just like looking at the graph.
They always had to be graphed.
Yeah.
Yeah. So either given a graph or given a function that you could graph on your calculator.
Or like a table.
Yep. So now we don't have to. We still have to have the function, but we don't have to graph it. So we can do it without a graphing calculator. So I think of this as two versions of each. So we have concave up, but this version, and concave up, this version. Do you guys think of it that way, or do you remember that from pre-calc at all? Here's what I mean. This slope is getting less negative, but that means it's increasing, right? This slope is getting more positive, but that also means it's increasing. And so if you think about it, I wish I had drawn that smaller, but if you think of just a parabola, it's a perfect illustration of both, okay? Both sides, okay? And then concave down is the opposite. So this is getting less positive, so that's decreasing. And then, what's the other one? This way, more negative. So that's also decreasing. So a parabola with a negative a value is good description. Okay? So what is f prime doing? Let's just use a parabola. It takes care of both. Obviously it's concave up. But in a parabola, what is f prime doing as we go along the parabola? F prime. Okay, so it's increasing. I think that's enough. So if f is concave up, f prime is increasing. What's another name for f prime that you can think of? Yeah, it's the slope.
The slope.
Slope of the tangent, right? I think sometimes it's helpful to always bring it back to that. And then if f is concave down, f prime is decreasing. That all seems good, right? But that's also all stuff we've done too. So here's the new part. We can take the second derivative, and if it's positive, that means it's what? Concave up. And if it's negative, it's concave down. So do you see how that makes this a little, or can make it a little bit faster? Because as long as the derivative is doable, the second derivative, we can probably speed up the process a little bit. I'm just going to write that because sometimes it's nice to see it as a word. So, sine curve, lots of, in an interval of the sine curve, there's lots of concave changes, right? What do we call those changes in concavity? Yeah, so we'll do that here pretty soon, but so like that one changes, those are points of inflection, right? Tell me about just thinking about the derivative. So if I took the first derivative on this interval here, first derivative would be what? Negative. Oops. No, wait. First derivative would be negative. What would be the second derivative of that on that interval?
So we can get it.
True, I like to think of it that way too, like velocity and acceleration.
And that's when you're approaching your,
It's slowing down.
oh no, it didn't.
Slowing down, going negative.
Because look,
It
it's
would be-
steep and then it starts curving.
Yeah, I see what you're saying. Okay. And then what were you gonna say? Okay.
Just,
Good. And then here would be 0, the first derivative. What would be the second derivative of that?
Also,
yeah. And it'd be known as, wait,
If it's 0,
because if you took the derivative of 0, it'd be non-existent.
yeah. Anyway, you get the idea, right? So we'll do some more of that with a different curve in a second. So in terms of finding intervals of concavity, what is our process, do you think? Just with a function.
Find,
the second derivative.
Okay.
Switches. No.
find the first derivative and find your inflection. So,
Okay.
where your first derivative equals,
What do you think where your second derivative changes signs?
Yeah. Those are points of inflection where your second derivative changes sign. Okay. So let's find those. This is a nice easy one. First derivative.
oh,
Good? Okay, so what do we do from there? We have our derivatives. Okay. So 3x squared minus 12 equals 0, or x equals positive or negative 2. Okay, why did we solve for the zeros? Yeah. We have to make a table. Everybody's favorite. This is, I think, the fourth process that we have to do tables for. I think so, because we did it for increasing and decreasing intervals. We did it for local maximum and minimum here. Maybe it's just the third. Anyway. Alright, so sine of f double prime somewhere less than negative 2. So plug in some giant negative number. If we did negative 100, this is what sign? It's definitely positive. Okay, between negative 2 and 2, if we just plug 0, it's going to be negative 12. So negative. Somewhere a really big number, positive. How about that? Still positive, right? Okay, what does that tell us?
that means that at x equals 18, the graph is concave down.
But, okay, sorry, go ahead.
No, the graph is concave down, negative 2, and then x equals 2, the graph is concave. Or f of x is concave.
Well, we need to give intervals, though, where that happens, instead of just at single points.
Oh, I see what you're saying. So from like negative infinity to would it be from -2? I guess, yeah, because we don't know
Are we good on the concave upness part? Negative infinity to, so f double prime is positive anywhere along there up to -2, right?
Yeah.
Okay. What are we gonna probably think happens at -2? Okay, so we'll have to be careful, but yes. Anyway, and then where else?
And from -2 to 2, the graph is going to be, for f of x is going to be.
Okay, good.
You need a -2 on the.
Alright, I lost my negative right there. And then our reasoning is why? Because
At the double prime.
changes sign on at -2 and +2. Cool. So what do you think of that compared to the pre-calc version? I mean, it was nice to just look at a graph, let's be honest.
Yeah.
So it's a little bit more work, but it's also more versatile, right? What were you gonna say?
Oh, no, I was just saying it's easier just to cut a graph.
Yeah. Especially instead of doing a sine table.
But then, when we did this in pre-calc, this was like, what, and here's the point of inflection, but you guys will find that in calculus. You wouldn't
Really?
explain- Yeah, you just wouldn't tell us what it means, you just like, I don't know,
Which teacher was that?
Mr. Yost.
Oh, that's funny. Alright, so there is a point of inflection of f at x equals c if it is defined, so we have to make sure that's true, and if f double prime changes sign. Okay? So, where the graph, how would you say that in simpler words?
Where the graph like changes which direction it's like separating.
Yeah, or we can just say changes concavity. But yeah. Okay, so flip over because there's some common mistakes there that we definitely don't want to do. So the first one is if we assume that f double prime equals 0 means there is a point of inflection, because it may not. Or assuming that f double prime does not exist means there's not a point of inflection. Or if it's not 0, we could also say it that way. So I definitely could see number 1 happening. So we have to put a star here. We have to make sure that we're not thinking that way. So these kind are really common on AP, on the AP test. And I like to let you guys know those kind. So we're either given f prime or f double prime. Before we even do it, what are we looking for on f prime to know if there's a point of inflection?
Change
What?
of slope,
Okay.
your sine of your slope. So like from going down.
Yeah, so from the increasing to decreasing or vice versa. So f prime. Where are the points of inflection? Okay, why -1?
Like the loss, like the, this one, other way.
Yep. Where else? What did you say? I heard -1, that's all I heard.
Yeah,
1. How about 2?
This
Good? Okay, and then it says state the intervals of concavity. So which direction would it be concave on this interval? What'd you say? Down? Good. Okay, I'm just gonna make a list. So negative infinity to negative 1. Where else?
1 to 2.
1 to 2. Okay, and then concave up on the other intervals. So negative 1 to 1. And then 2, 2, 3. Okay, how about f double prime? What are we looking for? Actually, before we do that, maybe let's just give a generalization. We're looking at slope. How about over here? What are we looking for?
Find your x-intercepts.
Okay. So looking at the sign, right? On the interval. Okay. How about this one? Points of inflection.
X equals -3. X equals 1. X equals
2. All right.